In this video we're going to look at how to calculate the correlation coefficient for a set of data and also to investigate some of the simpler properties of the correlation coefficient. Now we in fact had a look at this example of data back in our work for the statistics component of the Maths Unit 2. And what we've got here is the high and low share prices from 10 electronics companies during the course of a 12-month period. And we, in the course of our M2 work, we used GeoGebra to generate a scatter graph and the summary statistics for the data. So we've got the output from GeoGebra showing the scatter diagram for the data together with the summary statistics. The value R in the summary statistics is the correlation coefficient for the data, which is also known as the product moment correlation coefficient. And it's also known as Pearson's correlation coefficient for the data. If the data you've got is all the data from a population, then the value of R is the correlation coefficient for the whole population. More often though, the value of the data that you've got will simply be a data obtained from a random sample taken from the population, in which case R isn't a particularly good estimate of the correlation of for the population data. That better estimate for the correlation coefficient for the whole population is given by rho. So if the data given at the top that you've been analysing is a sample from a population, then rho is the resulting estimate of the correlation coefficient of the population from which the sample was taken. Now the calculation of the product moment coefficient of linear correlation, in other words the calculation of the correlation coefficient, has a rather nasty formula for it, which we don't in fact need to know at this stage, but that is the rather nasty formula. It's important though that we do understand one or two of the fundamental properties of the correlation coefficient. First of all, R has no units at all, it's just a number. Secondly, the value of R will always lie between -1 and 1. The value of R will equal 1 if and only if all the points lie on a straight line of positive gradient. The value of R will equal -1 if and only if all the points lie on a straight line of negative gradient. If the value of R is very close to 1, then that will mean the points are very close to a line of positive gradient. If the value of R is very close to -1, then the points are going to be very close to a line of negative gradient. So if R is close to 1 or close to -1, then there is a good straight line fit to the data. If R is close to 0, then there is not a good linear fit to the data. The value of R can be easily calculated on your calculator. So going back to the data we looked at the beginning of this video, we've got the scatter diagram presented again here. And now if we use our calculator, we can go through the process of evaluating the value of R. So we need to set up from menu 6, and then we need to go 2 to say that we want to have a look at the best line fit that we can get and also the correlation coefficient. We then start by putting in all of the X values. So those are the first pieces of data. So 355, 63, 202, all the way down until we've got all of the X values for the data entered. Once we've got all of the X values in, we need to go across the Y column and go back up to the top of the Y column and then enter all of the corresponding Y values. We now go to the Option key and go number 4 for the regression calculations, and there we can see that we've got the equation of the best fit line as being minus 4.67 plus 0.58x, and underneath we've got the correlation coefficient as being 0.982. So what we've got here is the correlation coefficient is 0.982 and the equation of the best fit line is y equals minus 4.674 plus 0.5808x. Now when we've calculated correlation coefficients, it's important to take care what conclusions are drawn. It must always be remembered that all it does is give an indication of how close the points are to lying on a straight line. So the conclusions that we can legitimately make are, if r equals 1, then all of the data lie on a line of positive gradient. If r is very close to 1, then the data points are closely packed around a line of positive gradient. If r is close to 0, then there's no straight line approximating the data points. If r is close to minus 1, then the data points are closely packed around a line of negative gradient. And if r equals minus 1, then all of the data points lie on a line of negative gradient. It's really important, though, that we take care to avoid misleading conclusions. If the correlation coefficient is close to 1 or minus 1, then it simply suggests that there may be a linear relationship between the two variables. We must take care to avoid suggesting that a value of r being close to minus 1 or 1 implies causation. So, for instance, if we were to do a collection of data about the weight and height of babies, then we would certainly have a correlation coefficient which was quite close to 1. It doesn't mean, though, that a heavy baby is heavy just because it is tall. If there'd also be a high positive correlation for data showing the average expenditure of households on holidays each year for the last 10 years, and the number of electric cars on the UK roads over each of the last 10 years. It would, though, be ridiculous to suggest that greater expenditure on holidays causes an increase in the number of electric cars. The amount that families spend on food each year would also show high positive correlation with the amount that they spend on energy each year. It would, though, be wrong to conclude that spending a lot on food causes people to spend a lot on energy. The correlation is probably much better explained by reference to the fact that inflation will cause both of these variables to increase. So we must be careful to avoid saying that large values of R that are close to 1 or -1 implies some degree of causation. Now, what I'd like you to do at this stage is just to pause the video and use your calculator to find the correlation coefficient for the data shown in the table here and the scatter diagram. So pause the video, do the calculation, then start the video again. This set of data actually has a correlation coefficient of 0. But clearly, if you look at the data points, the points lie on a curve. They actually lie on a parabola. So if the correlation coefficient is close to 0, then we simply conclude that the data is not closely packed around a straight line of positive or negative gradient. There may well be some non-linear function that can be used to describe the data. Now again, we've got a second exercise for you to use your calculator on. So can you pause the video and use your calculator to find the correlation coefficient for the data shown in the table and this particular scatter diagram? Once you've done that, start the video again. Now in this case, you will have obtained a value for the correlation coefficient that is very close to 1. But that is due to the fact that if you look at the scatter diagram, we've really got two distinct clusters of data points. So it suggests that we've possibly got two distinct populations being combined. And the fact that we've got two unlike populations being combined has led really to the creation of this high correlation coefficient. So when you're working out a correlation coefficient, it is well worth having a scatter diagram to look at as well. Okay, so we've introduced the idea of the correlation coefficient. We've seen how to calculate it, and we've seen one or two of the errors that we might make when we draw conclusions from correlation coefficients.